Welcome to another episode of Zeroing In. I'm Naman Jain, and hosting this episode with me today is Fenil Shah, who recently graduated from IIST with a master's in solid-state physics. Joining us today is a physicist who is currently an associate professor at the Indian Institute of Space Science and Technology, Trivandrum. He holds 2 doctoral degrees in the disciplines of physics and electrical engineering, wherein he carried out his doctoral work at the Leiden University and the Twente University of Technology in the Netherlands, respectively. He has extensive industry experience in numerous frontier research projects, rightly lying at an interdisciplinary juncture of his unique expertise, such as the development of dielectric thin films for gas sensing, the characterization of materials with high dielectric constants, and advanced work in the development of high-density capacitors, to just name a few. Following this, he moved into academia, wherein he held a research position at the Nanyang Technological University in Singapore, and then finally took up the position at the Indian Institute of Space Science and Technology in Trivandrum in 2013. To date, he holds 12 patents to his credit. His primary research interests lie in the futuristic and intricately associated fields of semiconductor physics, device physics, and nanoelectronics, solid-state physics, and process technology, which he addresses at his laboratories in IIST. In our conversation with him, we discovered his enriching outtakes from this intriguing journey, delved into the depths of path-breaking ideas that he's worked upon, and over the course of this path, how connecting the dots makes all the more sense. Join me in welcoming Dr. Jinesh K.B. Pillai. Welcome, sir.
Thank you. Thank you very much.
So I think we would like to start with this idea about your early years and what do you think were your role models like? Do you think that idea has changed over the time and how your passion of science has evolved over these years?
Okay, thank you, Naman. You started with a difficult question, I would say, because it's about the evolution of the interest from earlier days. So earlier days, of course, in childhood, we don't know what is exactly going in the field of science and research, what is happening all around. We have only a little bit of gist of whatever we are gathering from resources, from our teachers primarily. Naturally, in our childhood, what we think about science is quite different because at that time we imagine about science and now we live in science. Definitely, there's a big evolution in it. So when we imagine about something, we can add all type of fantasies to it. We can start from atoms to black holes, anywhere we can go. But when you live in science, we have to deal with it. See, there are a lot of different ingredients to it when you grow up from your childhood dreams. Because as I told, imagination is beautiful. We can add everything. And when you start adding reality to it and you slowly understand that what you're learning so far was a science fiction. And now we are removing that fiction part. Our experiences in different groups, different research environments, and maybe in industry or academia, everything will add up to it and it will finally make what you are today. Okay, so that's an evolution, definitely. Yes, quite different from what I was dreaming about it.
It's wonderful to hear how much science has evolved for you and in so many different directions as well. Along those lines, can you tell us how you first stumbled upon your interest in the field of science, or do you remember any peculiar stories from your childhood in this context?
I was born and brought up in a very, very small village, surrounded by paddy fields and coconut trees and all. So there was not even a concept possible to become a scientist because that was not even in our ideas, okay, dreams. It all happened because of a book which I was reading at that time. I accidentally happened to have a book which was called Our Great Scientists. So that book, I believe it was published by Kerala Shastra Sahitya Parishad. They are actually spreading science in Malayalam in Kerala. That was a book which was describing about different scientists in one page, from their birth to all their achievements. Mostly Nobel laureates and a lot of scientists from India. Okay. And it included all fields, including psychology. That was an amazing book, and we have to be fortunate to get such a book at that age. I think I was in the 7th standard, maybe 12 years old, because you are suddenly exposed to a bunch of different fields in science. I hadn't even heard about many of those fields at that time. At that time, science means science. Okay, that one single book contains physics, chemistry, biology, and everything. So from that, I came to know that, okay, there are different fields in science. At that time, it was too early to decide where to go. So that book actually initiated a kind of passion in science.
Yeah, that's really nice to hear. So, continuing from there, we'd like to ask you, how you transition from your school days into bachelor's and deciding to pursue a master's as well as a PhD. So, could you just briefly take us through that journey and what crucial decisions you were needed to take at those junctions?
Okay. When I am going to the pre-university, conflict comes. 15 to 18 years is an age of conflicts in everybody's life. We struggle to take decisions. So at that time, a little bit of interest in literature came up. Then I was actually concentrating more on Malayalam literature than science. So science passion was there alongside. But then what happens when you go to pre-university, suddenly modern Malayalam literature came into picture. I was totally trapped into that. So passion for science was kept away a little bit. Then there was a big conflict where to go for literature or to science. And then I understood that finally my grades are getting lower. Then I had to take a decision where to go for science or literature. Then I decided to go for science, and then I joined bachelor's. But again, at that time, everybody wanted to go for engineering. But I actually wanted to go for BSc, Bachelor of Sciences, and then to MSc like that. Again, I got this idea mainly from that book, how people were actually doing science. But I mean, naturally at that time, everybody was against joining science, basic science. Everybody wanted me to join for engineering. With their compulsion, I wrote the engineering exam, and unfortunately, I passed that exam. So the pressure was enormous to join for engineering. At that time, my literature passion was kept aside. I decided to go for science. Whatever happens, okay, I will take the responsibility. It's my life, so I have to take my responsibility of my decision. So, yeah, there were a lot of oppositions, a lot of struggles, a lot of problems were there, but finally I managed to join BSc Physics, and then onwards things were happening, just happening as I was thinking about it. In the BSc, I joined Mahatma Gandhi University in Kottayam. So there my teachers were, I would say, excellent. They were really passionate about teaching. So that shaped up my career towards physics, I would say. So then I went for a master's in Cochin University of Science and Technology. Again, I got an excellent opportunity to work with eminent professors there for my projects. So I could do projects earlier than the time it was actually allowed to do projects, and that helped a lot. And we could publish 3 international papers from master's projects. So that was really an achievement. And at that time, nanotechnology, nanoscience, nanomaterials, that field was coming up slowly. So I'm talking about 20 years ago, 22 years ago. Okay, that was happening. So I could do actually substantial work in nanomaterials. And that helped me a lot to gain my passion again in science, in research.
I mean, now I probably a little clearly understand what was the thing that struck out for me. It was the fact that, normally as children, we imagine that, we have this exposure, and then we have these role models that we want to always go after and become like. And you had this innate sense of passion, or this innate drive somehow that, when you find something, you actually go after it, and then you go ahead with it. Because it's not about being the first, it's about being someone out of all this place where you've not seen someone doing something like this, So that's what strikes out in this whole idea.
Yeah, as I told you before, I mean, for example, exposure to that particular book, I kept those books with me for a very long time because I was reading again and again and again. I don't know how many times I read the page which contains Albert Einstein, Fermi, and C.V. Raman, and Chandrasekhar, of course. These 4 people, it was amazing. So I discussed these things with my friend, and we discussed and we decided to make a lab at our home, and then basically stealing chemicals from kitchen. Okay, and Kottayam is very famous for latex, rubber. Okay, so we have plenty of rubber trees around, and to process the rubber sheets, there's a chemical used which is formic acid, and that will be there in every house, mostly in Kottayam. Okay, so we used to steal formic acid. That's a very strong acid, by the way. So we take that acid, We take some washing powder, we mix it, and we see, okay, a lot of bubbles are coming up. So this kind of simple experiments we started doing. All those things helped me a lot. I think my father gifted me a set of test tubes. Okay, and that was with me almost until I was doing masters. Okay, so that was like the primary science gift or science inspiration, because that test tube is something. Boy of that village is something enormous. Okay, so every ingredient helps a lot to shape up our goal towards a career. Okay, science was not just a career for me. I was not even thinking about a career at that time. It was just about doing something passionately, something of your dream. Okay.
Yes, it's really, reassuring to hear how such small things, if you have passion strong enough, even these small things can, keep you going throughout. Like, as you mentioned, small one-page introductions of great scientists and your father gifting you a mere test tube. You just require that small of an incentive to carry on with your passion. So it's really good to hear that.
So I would like to jump here a little towards a more technical side. So we tried taking a glance at your PhD thesis, which was, to be honest, quite an intimidating piece of work. And there we came across this idea of thermolubricity. And we believe this concept was introduced for the first time, or in a sense, say, discovered in your work. So could you tell us more about this idea and how you stumbled upon it?
Sure. Yeah. So when I went to Netherlands, when I went to Leiden University, I heard about this particular project about friction. So this is called nanotribology. Tribology is a field of studying about friction. So nanotribology means friction at nanoscale. I mean, we know friction is we can say the most ancient scientific problem. Okay. So because starting from the first rolling thing, friction is one of the first scientific problems. But to be honest, only in 1930s there was a first model about how friction comes in physics. Okay, so that's called Tomlinson model. Actually, that model is saying that when you rub two things past each other, the nano asperities, like clusters of atoms, how they are behaving, where is this energy dissipating? Because friction is something which we cannot retrieve, it's an energy which is dissipated. So how this friction is coming? Where is the origin of friction? That was that problem. It has a very important technological aspect, because when you deal with nano materials and they're moving, so we are now miniaturizing everything. Everything is coming down to nanoscale. So we have micro electromechanical systems, MEMS, and it has a lot of applications we know. And it is again miniaturizing because it is becoming nano electromechanical systems. So our gearboxes, everything becomes nanomechanical in future. So then this question will come: where is this friction coming from? Is it from one single atom or group of atoms, or how atoms give out this energy, or they dissipate this energy? So that was that question. So for that, we had to develop instruments which can actually measure the forces between atoms. So we developed, actually, my senior already developed a very sensitive atomic force microscope which can measure the force between atoms. And then I joined, I continued his work. Then we understood that anyway, if there is temperature, we know atoms are vibrating, and vibration of atoms. So they can actually, if you put one atom on a surface, it can jump over because it has temperature, it has thermal energy. So what will happen if two nanosystems are moving each other, and what is the role of temperature there? So when we analyzed data we got from those experiments, we understood that temperature is like a lubricant, because it basically helps atoms to overcome the atomic barriers. So at higher temperature, these nano systems will have easy movement, lubricated by temperature. So that is the concept called thermolubricity. Okay. Again, to prove that, we used the theory by Tomlinson, which was in 1930s. Okay, so it was an old theory, but it is still valid, and it's a wonderful theory. So using that, we could predict what will happen if temperature rises, and then we experimentally verified it. Okay, so lubrication by temperature. So that was the thermolubricity.
So we'll just want to continue on the line that you were answering the last question, that this idea, this concept, the whole concept of thermolubricity is something that you proposed in your PhD thesis. It was not there before, really. How does one go about in proposing something really so fundamentally relevant? How is that excitement like? Because I mean, right now when we hear about PhDs or the people who are pursuing PhDs, they're mostly under pressure, or they're also like having pressures of presentations, producing something, all of these things coming together. But then to have a space of mind and the work to be able to produce something and then be passionate about it, even at the end of PhD, to work for another PhD, that's a completely different ballgame we cannot imagine. And this thing is also, I think, very common from our childhood, that we understand that you were always this dreamer who had these ideas. It's just that you needed a point to touch, and you would go after it rather than thinking about if I can do that. So we just wanted to ask you more about this work, doctoral work that you did, and what did it entail for you?
So when you start with one work and finish a PhD, there will be something more exciting to be done, and that becomes another PhD topic. Like that, it goes in a lab. So when I joined it, it was actually the purpose was actually to find out where is the origin of friction from atoms, and then analyzing the data, we understood that there is a lot of thermal noise in it. Okay, so that noise could be something useful. Noise is always not bad. Okay, not all the noises are bad, but sometimes noises are good. If you can analyze the noise, any kind of noise, you can use it. Okay, for something. So this thermal noise from our instrument, we thought that, okay, it would be a great idea to analyze it and then increase the noise. Okay, how we can do that? By just increasing the temperature. Increase the noise and see how the system behaves. So that was the initial idea where we got the idea that temperature might be a lubricant acting, because we saw that the friction is reducing, the energy dissipation is reducing, because the system, they are trying to adjust here and they are going into a kind of chaos, and then we see that friction goes down. Okay, but something very unexpected happened in between, because it was Netherlands, and Netherlands is always rainy place. 365 days it rains there. Okay, so humidity is very high. So I was not doing any kind of humidity control in my experiment. So suddenly we thought about, okay, we have to control the humidity also in the lab, in the environment. So when we control the humidity, we understood that something is happening in the friction. So we again increased the humidity, reduced the humidity, so changed the humidity very step-by-step manner. And then we understood that something else is going on. It is not just friction between two surfaces. There is water getting inside in this nanoscale asperities. So in my experiment, it was a very sharp tip of tungsten, which was actually moving on top of well-polished graphite. So to see what is the friction between tungsten and graphite. But suddenly we understood that water also is getting in between. And even at a room temperature, water becomes ice because it's a nanoscale asperity. And it is like to move ahead, we have to break this ice. And then again, it forms ice, break that ice again. So we could clearly see the lattice of ice just breaking and forming, breaking and forming in between. That was a revolutionary thing. Okay. So that was, from temperature, suddenly...
You just say it so easily. It's what is evolutionary.
Yeah, I mean, it actually took a lot of efforts, because when I suggested that it looks like the ice formation at room temperature. Okay, then my supervisor suddenly jumped out of his chair and said, "It looks exciting, but I need proof." So he came up with the suggestion that, okay, bring all your data and we will analyze it. So we had a very, very long oval-shaped discussion table there in our meeting room. What I did is that I printed out all the data, all the graphs, and stacked all along the table side. And we just went through one by one. And my supervisor was saying that, okay, if this is ice, that should happen. Where is that data? Okay, then we run to that data and take it. As I told you before, a PhD time is a polishing time. Okay, it's how difficult a PhD is, in my opinion, that will be how nicely that person will be polished. So my PhD was like that, because my supervisor did not allow anyone to publish any paper until a complete picture, the complete story is there, and its evidence is there. Okay, strong proof is there. It is not like you are doing an experiment, take the data, publish it. It was not like that. We will get a publication almost at the end of the PhD time only. Okay, we do not start publishing from beginning itself, because you need a complete story, then divide that story into papers. That was the structure, the style there. So that helps a lot, because finally, if you publish something and after 2 years you are getting a result which is against it, you'll have a problem. Okay, because you already published something wrong. So that will not happen if you have a full set of data and full evidence for it. So that's why my supervisor, Professor Franken from Leiden University, he's well known in the field of scanning tunneling microscopes, surface science basically. So he said that this is the way we are doing. Okay, I need proof for everything, and then we will publish. So finally, I could convince him. That was a very difficult process, but that is the part of that polishing process. Could convince him that there is ice at room temperature. Okay.
Wow.
So from temperature and thermolubricity, finally it became friction of ice at nanoscale. That is again the evolution of process in a PhD. So I used to tell my PhD students also that, okay, we start with a project, but keep all the doors open. We never know where where you end up. Okay. Within the restrictions of that topic. Because if I restrict anyone, any student from thinking, the horses are traveling. I mean, the horses have this face mask. They can only see front side. They cannot see sides. Okay, they can only go in a line, and that line is already that path is already made. So that is not the correct way of doing science. There should be path. The horse should find out the path. Then you'll get a lot of ideas.
So I'll like to continue further from here, going back to the timeline that we were discussing after your PhD days. Sir, as you pointed out, the idea of thermolubricity basically came from noticing the noise and noticing that it did affect friction. So it's like going back to the roots of science. Like, observation is the first step, and people usually term these kinds of discoveries as accidents, but it really isn't accident. You need that observational skill and to identify that this is something good, and that's what science is all about. So along those lines, I would like to ask, how do you go about the process of choosing topics in the field you're working on? And I mean, as you pointed out, you really have to be open about everything, and you don't have to look in a straight line. So if you could just briefly explain.
Yes, definitely. So science is all about observation and connecting your observations by logic. That's mainly what we do in science. So we have certain logic. We need evidence for that. We do experiments to prove that logic works. And then it will ask many questions. That experiment will come up with questions. And then we have to connect them again. So again, you see, I love the word evolution because it's all about evolution. You see, one problem we start with, but it evolves to completely different sides. For example, after my PhD, I joined Philips Research, and my second PhD is actually related to dielectrics. So basically now my expertise is mostly on dielectric measurements. And suddenly there's a field which is called resistive memory. Okay, so it's about dielectrics used for memory purposes. So naturally, from a normal capacitor applications in CMOS, I jumped into memory, where basically again the same capacitor is used, dielectric is. That's what we are actually doing at the moment here in IAST. And there is a natural evolution from resistive memory. So what we can do with these kind of memories? And then we understand from literature that people have suggested that, okay, this kind of memory can be used for making artificial neurons, for example, just like mimicking the brain of living systems. So those kind of things, you see how it is evolving. We have to keep our mind open, our ways open, our doors open. Then different ideas come in, and then we have to see where we have to connect all these things together. Okay. So from dielectrics, now we are in artificial neurons, and then slowly entering into artificial intelligence. And it goes like that. Okay. We can restrict ourselves into dielectric physics, and we can do only dielectric physics. That's fine. There's no issue. But then again, as I told you before, we are like the horse with that mask. Okay. We don't see what is going on the other sides. So sometimes we should remove that mask and see what is available around, and we have to choose our own way. So that selection, at any point in life, that selection is very important. The path you are choosing is very important. So that's how we ended up with the neuromorphic. So a memory technology which is mimicking neurons is coming up. So we started with the dielectrics, but now we are there. Okay, that is evolution so far.
Sir, I would just like to ask you about, as you briefly also pointed out right now as well, about your research directions, right? The current research that you are pursuing in your labs, the multiple labs that you are actually leading at IST right now. And your investigations are inside these areas of material sciences, as well as there are so many bachelor's and master's projects that you've supervised, and they're actually very very well listed for us to look through on your website as well. And I mean, there's just, your research interests are so massive and fascinatingly forthcoming with these futuristic technologies and coalescing electronics and physics at the heart of it. So how do you choose your projects in this exciting soup that you describe? And I mean, what do you look further, and how do these ideas come together for you?
Okay. Just like I said, I really like the word soup because it's really a soup. Okay. It's a soup of all science in it. Because see, at a certain point in time, we cannot distinguish between engineering and pure science, or within pure science, we cannot distinguish between chemistry, physics, mathematics. So what happens is that if you start with certain ideas for applications, you have to do physics, you have to do chemistry, you have to do engineering. So what we are doing at this moment is about memory. And what type of memory? We are trying to mimic our neural networks, okay, our real neurons in our brain, which means that we have to know biology. Okay, so I have started studying biology a little bit. That means how neurons are working, how our brain is working. All those things we have to study. And then at the same time, we have to construct it. So we need material science. So we have to know what are the properties of materials with which we can make neurons there. And after that, once you make a device, we have to measure it. And measurement means now it is into electronics. Okay. So we need, one person cannot be an expert of all these things. So we are, again, you see, ingredients come up naturally. So we have to make this soup. What will be the taste of the final soup? We don't know. Okay. So when you're hungry, you take a spoon of it and eat it and be happy. That's it. So this is an evolving soup which we do not define where end of this cooking. Okay. Maybe end of our service here. So now, is it the end? Is this neuromorphic technology is the end of our research? We don't know. Maybe we'll leave it again from there, depending upon the interest of that time, or if there are no new ideas coming up. At this moment, memory means immediately memory, which is something we have. Okay. So how we have to connect that to electronics, how we can electronically come up with an idea of brain-inspired memory. That's basically what we are doing at the moment. To add that, maybe if I elaborate a little more, basically we are now living in the world of artificial intelligence, and I think that is something which is going to change the world completely. Okay, from my generation to your generation, the main difference I would say that is the availability of information through internet or through computers or whatever resources. Comparing to my time of your age, resources are very large now. I touched first time on a computer during my master's, okay, and that was with a black and white monitor and very less memory and all. Okay, so now you have your own laptops and everything. So I know what is Moore's law. That I was living in Moore's law. Okay, you can clearly see that. Now you see we are already in the 6th generation of computation, that is artificial intelligence, and you are going to see the applications of artificial intelligence more. So that means our computation also has to cope up with the artificial intelligence. Our present computers, the problem is that we take information from the memory, process it, and give it as output. So one bus control is there. So that is not what is happening in our brain. In our brain, neurons have many connections with several thousands of neurons that we call synaptic connections. And one neuron can connect to more than 40,000 other neurons. So that's why we are able to remember several things, and we are able to do parallel things at the same time. Because I mean, you see how many biological functions are happening in our body. At the same time, we are drinking, we are eating, we are hearing, we are seeing. Everything happens at the same time, which an electronic computer at this moment cannot do, because it's one-step process: memory processing output, memory processing output. So if we can do the same thing what our brain does with the neurons, with our computers, that will be revolutionary. That is the idea of neuromorphic computing. So the present computation is called von Neumann bottleneck. Von Neumann bottleneck means we can do one process at a time. But if you have parallel computers, we can actually do a lot of computation at the same time. That means if you have one computer connected to 40,000 computers, that is equivalent to one neuron in our brain. So IBM has come up with an experiment. They wanted to simulate some functions of a brain of a cat, and they had to use 1.5 lakhs of computer. Okay, so 2 supercomputers that has 1.5 lakh computers with 144 terabit memory. Okay, so that is the complication of our brain. But if we can come up with, again, the same computational power into one chip where we can do all these things parallel. So small chip where we can artificially create a neural circuit, that will be revolutionary. That will change the world of artificial intelligence completely. So our research is in that line, very, very small part of that thing we are doing. We are finding out new materials to create this kind of new memory which are useful for this neuromorphic technology. And what are the connections there? What is the physics behind their final working? This is what we are doing at this moment.
Okay. And so what does it take to, I mean, since you have like at the moment, I believe there are 3 labs that you are leading at the moment at IST as well. What does it take to, start a lab from scratch, and how do you take it to a point where you see now that it's working and there are things producing out of it, and you basically have been through it? So how is that process like, if you would be able to explain?
That is a very painful process in the beginning, because we start from scratch. That means we don't even have a test tube, which I had in my childhood. Okay, we started with a microscope glass that we can basically buy for a few rupees from a store. So we started our research with that, and then we had very, very, very few things in our hands. Then we started buying slowly, accumulating slowly, very slowly. And sometimes it is easy to make things than waiting for it or to buy it, because buying is always costly. If you make it, you know what you are making, how this instrument is working. So at this moment, starting from scratch, now after 7 years here, we have now 2 wonderful atomic layer deposition systems. One we constructed in IAST. So that means we know what we are doing, and we know how to modify it. We know what are the scope of it. So that's a good thing. Again, that idea is a part of the same evolution, because you see, we start with playing with the small things, and we started making things. That was like my childhood was like that. I mean, we have very small things around, and we have very limited toys. So we are happy with that. We make our own things. Making small sculptures out of mud was my passion at that time. Okay. I used to make small gods and goddesses and small creatures with clay. So this kind of skills will help in future. After your childhood, you will forget about it, but what happens is that those skills will remain in you, and you can make anything out of anything in future. So a lab will develop from scratch if you have small ingredients together, and if you can put them together. I mean, things will happen. So now we have mainly 2 labs. One is called Emerald, that is electronic materials and devices. That is where our memory devices, material science is happening. And another is we call STIC, that is space technology innovations and characterization. So there we do projects related to ISRO, mainly for space application. Okay. These are not 2 different things, but we separate them by their basic purposes. But we do research in both of them. So when we started with, when my first PhD student, Mr. Preetham Hasra, joined, basically I showed him the lab, and the lab was totally empty. 3 chairs and 4 tables were there. So that is where we started with. Always the first PhD students will struggle a lot. And then with his enormous hard work, we managed to get to the current level of our labs. Okay. So now we are happy. We can do a lot of things, doing a lot of things.
Okay. So probably we'd like to have a few conclusive questions now. I would like to ask you, so if the field of academia probably did not exist, did you have something as an alternative that you would like to go forward with? Or an alternate question would be, was there any other field of science that you wanted to explore that you probably did not get time to, but you really wanted to explore a different direction of physics or something probably?
If not science, I would have become a writer. Okay. That's the simplest answer.
Although we still believe that we can still read a novel from you probably 10 years down the line, but anyway.
Let's see. I don't want to surprise you at the moment, so let's see. So, but certainly, I mean, we have certain experience in science now. Maybe we should start writing science fiction. Okay. But along that line, I would say, as I told you, after my pre-university, when my academic credentials were totally gone, So I decided to turn into science. I simply took all my collections of all my writings so far and I just burned it with a determination that I will not look back until I reach somewhere. Okay. It's not, it was just a purely personal decision. I could have done the other way around also. I could have kept away all the science books and I could have gone for literature also. Who knows? That also would have been better for me. I don't know. Okay, so at that time, my passion was for science, so I just stopped writing and interest in literature and philosophy. So I turned in this way. So definitely, that's my answer. If not scientist, I would have at least tried to become a writer. And my still unfinished business or incomplete passion is actually to become a musician. I don't sing, but I love music a lot. I started learning piano a little bit, but because of the time constraints at this age. Okay, last year I started learning piano, but I stopped in 6 months. I stopped it. Passion is there, but passion and time you have to find out time for. Yeah, so scientist or a writer or a musician, I would have become.
Yeah. So along these lines, I would like to ask you one more thing. To let go of something you really really love and to choose something else that you love equally strongly, it takes a lot of determination and courage. Some word of advice you'd like to give young students like us who are currently at junctures where we need to make important decisions and choose between two or three things that we love. If you could just
Sure. If you have more than one passion which are equally strong, okay, the first thing to do is to do some homework and see where you will, what your heart says, basically. Okay, because it's important. If you take one and lose grips, that can be damaging. Okay, you will later on think, because I had equal passion for that. Why did I choose this? That question should never come. Okay, whatever you choose, you should with the full heart you should go for it. Then it will successfully. This is what I learned from the entire evolution story of my own career. Okay, so if you want to become a writer later on, you can become a writer later on, because writing skill or passion for literature is not something which you lose if you have real passion for it. But if you're a writer and if you want to become a scientist at the end, that's a difficult path. Okay, so certainly living out one of your biggest passion is a very painful process to take a decision. Where should I go? But you have to make your career safe at the same time without losing that interest in the passion or passion in the chosen path later on. So what I would say, no regrets later. You choose a path whichever your heart says, and think about future. The homework I said was, you have to do some homework to see what are your possibilities to succeed in that path. Okay, so that's important. From a philosophical point, I can advise you. Okay, you just choose your passion and then go for it. Okay, that's fine. But without doing homeworks, that will not be successful. So do a right homework in the sense that where you want to go. Do you have the resources to go in the field of your passion? And nobody can be completely sure. And what are the possibilities? You can judge yourself. That is my strong belief, and that's my philosophy. Because nobody knows me more than I do about myself. So only I can judge whether I will succeed in that path, whether I want to choose that path. All others are ingredients. All other advisors, from everywhere, they are all resources. Okay, whichever path you take, never regret about it, because you took it because you had that passion, and keep that passion going is the most important thing. And at the same time, try to keep the other passions along with you, but do not get interfered, because interference can come from any directions. Okay, you know what happens when light interferes? Light is a continuous thing, but it interferes. It has dark and bright fringes. Okay.
So you keep taking us back to your literature idea, and then how you use metaphors in such immensely fascinating way.
So avoid that dark regions, and then you are continuous in your career.
This was Zeroing In with Dr. Jinesh K.B. Pillai. It has been brought to you by the Sounding Rocket in collaboration with the IIST Alumni Association from the Indian Institute of Space Science and Technology. We extend our sincere gratitude to Dr. Jinesh K.B. for sharing his inspiriting journey, gravity of following along intuitive trails, and insightful outtakes from the diverse fields of semiconductor physics with us. On behalf of the whole Zeroing In team, which includes Shreya Mishra, Fenil Shah, Manish Chauhan, Prajwal Patnaik, KVNG Vikram, and I am Naman Jain. Thanks a lot for listening to this episode. If you have any suggestions, you can write to us on zeroingin@outlook.in or contact and follow us on our Instagram handle @zeroingin podcast or the Sounding Rocket page on Facebook. We hope to meet you on the other side of the week.